All right, here is our warm-up. It asks us to solve algebraically and graphically. Notice that this equation is solved for y, which means all of this can be substituted into y in the other equation, and that's what we're going to do. So we have the 2x plus 3 times y, which y equals 3x minus 1, and then that equals 8. So solving for this, I'm going to distribute the 3 right here. So I'll get 2x plus 9x minus 3 equals 8. Combining those x terms, and while I combine those x terms, I'm also going to add 3 to both sides. So I get 11x is equal to 11. Dividing both sides by 11 to isolate my x. Whoa, not, there we go. There we go. X equals 1. So that is my x value for the solution to the system of equations. But remember, when we're talking about a system of equations, we're talking about an xy coordinate pair, so we have to solve for y. And we can solve for y in any one of our original equations. This one's already solved for y, so I'll do that one. So we're going to plug in y is equal to 3 times x. Well, we just found that x, in this case, for our solution is 1 minus 1. So we get y is equal to 3 minus 1, or y is equal to 2. So the solution here to this system is 1, 2. That's our solution to the system of equations. Questions about algebraically solving this system of equations? Morning, Angela. Glad you're here. All right, we're going to solve graphically now. I'm going to graph y equals 3x minus 1 first. It's already in slope-intercept form. Our y-intercept is 0, negative 1. We get that right there. And our slope is 3. So that means we go up 3 into the right 1, up 3 into the right 1, up 3 into the right 1. We can also go down 3 into the left 1, down 3 into the left 1. So those are where the places where my points are going to be. And there's my blue line. My red line is not currently solved for y. It's not in slope-intercept form. So we're going to have to do something to it. We could convert it to slope-intercept form. That's fine. We can also do something like this. I'm going to first, well, I'm going to find my x-intercept. And I do that by plugging 0 in for y. So 2x plus 3 times 0 is equal to 8. And this is 0, so I just have 2x equals 8. So I'm going to divide by 2, and I will get x is equal to 4. So that means that I have the point 4, 0 on my line. You know, I have a kind of a tricky way of graphing this. Do you want to see the little bit of a tricky way? It's nice. I like it. Yeah, Josh. All right. So I know that this point right here must be on my graph because I solved the system of equations. And as long as I solved it, this coordinate point has to be on both of them. So I could just say All right, well, I know that 1, 2 right there is on my graph. I'm done. All I have to do is to connect those two lines. That was a really sloppy connection. But so that's one thing I could do. But just to be more thorough, I'm going to find my y-intercept by plugging in 0 for x and solving for y. Well, this is equal to just 3y because 2 times 0 is 0. So I can divide both sides by 3, and I get y is equal to 8/3, which is 2 and 2/3. So 2 and 2/3. So that's the point. The point, 0, 2 and 2/3, which is about right there. So then you can see that if I connect my red points there, it's going to look like that, and that's great. And so that's what I'm going to do. The other thing I can notice is that my slope here has to be -2 over +3. So I could go up 2 to the left 3, and there would be another point. Any of those ways of doing it are just fine. That is not a very straight line, but I wouldn't dock you for it, and I hope you don't judge me for it. Questions here before we move on from the warm-up? We started out with a linear system of equations in the warm-up. Now we have an nonlinear system. At least one of our equations is nonlinear. So this says to solve the system graphically. So all we need to do is graph the two equations. This right here says that my y-intercept of my parabola must be at 0, -1, right there. And now I'm going to make a table. I could try to does it factor? It does not factor. All right. So I'm going to make a table. And when I'm making a table, I'm going to plug in an x value and find the y value. If this trips you up, ask me a question, okay? So the first point that I found was 0, -1, because when I plugged in 0 right there and right there, this is 0 squared, which is 0, minus 2 times 0, which is 0. So all of that is 0 minus 1 is -1. So we plugged in 0 for our x, and the result was -1 for y. So we got that point right there. We're just going to do that same thing for different x values now. So I'm going to plug in a +1. So we plug in 1 there and 1 there. 1 squared is 1. Minus 2, because 2 times 1 is 2, so minus 2. So all of that is -1. -1 minus 1 is -2. So now we can add the point 1, -2. Now, here my a value is 1. That means that my graph has to look like this, opening up. That means it's got to come down here somehow, somewhere, and then it's going to turn up. Okay? So I'm going to move to the right one more unit for my x value and put in an x value of 2. Plugging in 2. 2 squared is 2. 2 minus 4. 2 minus 4 is -2. Oh, 4 minus 4, excuse me. 4 minus 4 is 0. 0 minus 1 is negative 1. Sorry about that. I think I said that incorrectly at first. Let me go back and do it again. 2 squared is 4. 4 minus 4 is 0. 0 minus 1 is negative 1. So when x is 2, y is negative 1. And right there, because these two have the same y value, the x value that's in between them must be the line of symmetry, which means this must be the vertex. I can also see that because my a value here is 1. So from my vertex, when I move to the left and the right 1 unit, I go up 1 unit because 1 squared is 1. Similarly, when I move to the left and right 2 units, 2 squared is 4, so that means we go up 4. 1, 2, 3, 4. And 1, 2, 3, 4. And there are other points. And now I can graph my equation, graph my parabola. Not perfect, good enough. Questions about graphing that? All right, now we're going to graph the line. My b value here of positive 1 tells me that I have a y-intercept at 0, 1, right there. And my slope is negative 1, which means I go down 1 to the right 1, down 1 to the right 1, or up 1 to the left 1. So I'll put those points in. Now I can connect those points. And I can see that my solutions to the system are the points negative 1, 2, and 2, negative 1. Questions on graphing that system? We're going to take that same system now and we're going to solve it algebraically. And hopefully we're going to see that our two solutions, when we solve it algebraically, are the same as we found graphically. Otherwise, something went really, really wrong. So to solve this system algebraically, we can see that both equations are equal to y, which means we can use substitution and take this and plug it right in there for that y. So that basically we're just setting the two equations equal to each other. Some people call this the equal values method because they both equal y, but really I just see it as a special case of substitution. So I've taken this and I've substituted it in for y right there, and then I wrote the result out. Now, whenever we have a quadratic, we pretty much have to get everything on one side of the equal sign and then have it equal 0. So I'm going to move everything to the left by adding x, subtracting 1, subtracting 1. So I get x squared minus x minus 2 equals 0. Now here, when I look at this equation, I notice that it can be factored. And factoring is the quickest way to solve this. You could also use the quadratic formula, okay? But I think factoring is the fastest way to do it. So You could use the rectangle and diamond method, or just go straight to the factors if you're able. What times what equals x squared? X times x equals x squared. Now, the signs that go there and there, they have to multiply together to give me a negative. And the only way for that to happen is to have one of them be positive and one of them be negative. Now, this times that has to be -2, and add, so these things have to add together to give me -1. And it's going to be -2 and +1. Now this right here, I'm going to do all the steps, okay? Because I have two things in parentheses there, two binomials, when I multiply them together, the result is 0. The only way for that to happen is if either x plus 1 equals 0 or x minus 2 equals 0. This is called the zero product property. If you have two things that multiply together to give you 0, either the first thing has to give you 0 or the second thing has to give you 0. So now we can solve these two equations to see, well, what does x have to be in order to make this 0? And what does x have to be in order to make this 0? So that's the general idea we're working with here. Subtracting 1 from both sides, I get x equals -1. Or adding 2 to both sides, I get x equals 2. All right? Questions so far? I've done quite a few things there. Does anyone want to ask a question here? We're not done yet. Okay. If x equals 1, I need to find out what the y value is. And I can use either one of my original equations because what we're finding is an xy pair that makes both of them true. So with the same x pair, you have to get the same y result. I always use the easier of the two equations. So I have y is equal to negative x is -1 plus 1. That's going to be y is equal to 1 plus 1. So y is equal to 2. And here, then, our solution is x is -1, y is 2. In this case, whoops, y is equal to -2 plus 1. And that's just y is equal to -1. So our solution is x is 2, y is -1. X is 2, y is -1. So our two solutions are -1, 2, and 2, -1. -1, 2, 2, -1. Yay, we got the same answer for both of when we did it algebraically and graphically. At home, if you're watching this on YouTube, you should pause the video, take a break. We are going to pause and take a break as well. Here we have a system of equations that it asks us to solve it algebraically. So again, we're going to use substitution. Take this, plug it in for y. So we have -2x squared plus 16x minus 19 is equal to 18x squared minus 144x plus 121. I think some folks when this problem shows up, some people might feel anxious because of the size of some of the numbers. It's okay, they're just numbers. The problem is exactly the same from the point of view of the process. Move everything to one side and solve for x. I have a preference for positive a values in my quadratics. So here I'm going to move everything to the right. I'm going to add 2x squared. That way I end up with a positive a value. I'm going to subtract 16x, and I'm going to add 19. And I can do that all at once. If you'd like to take multiple steps to do that, that's perfectly okay. If you want to do it all at once, that's perfectly okay as well. So we have 0 is equal to 20 x squared minus 160 x plus 140. Now, when you look at that quadratic, what do you notice? What do you notice about those? They're all divisible by 20. Yeah, great, great. They are also divisible by 10, but we want to take the greatest factor. And so we're going to factor out the 20. So we have 0 is equal to 20 times the quantity. When we divide this by 20, we just get x squared. When we divide this by 20, we get negative 8x. When we divide this by 20, we get positive 7. Now, when we look at this, when we're solving for x, if we divide this whole side by 20, we are just left with what's in the parentheses is equal to 0. So when we're solving, we can just kind of ignore that 20 for the most part. And when I look at this, I see that that's factorable. Again, so I have 0 is equal to 20 times the quantity. What times what is equal to x squared? X times x is equal to x squared. Now for my signs, when I multiply the two numbers, they have to give me a positive, but when I add them, they have to give me a negative. The only way for that to happen is to have two negatives. So what times what is positive 7? And when I add them together, I get negative 8. Well, the only two things that only two whole numbers multiplied together to give me a 7 is 1 and 7. Okay. Now, over here, I went through this whole process here of the zero product property. But notice that my result here really just asks, what do I plug in there that will make this equal to 0? And the answer was negative 1. And what can I plug in here that will make this 0? And the answer was positive 2. So I am going to skip that kind of easy step and say, okay, well, what can I put in there for x that will make that 0? Well, x must equal 1. And what can I plug in for x there that will make this 0? Well, x has to equal 7. And that's a perfectly fine way of doing it as well. Okay, either one of those work. If these binomials are more difficult, well, you might need to go through that process. Or go through it if you want to, either way. Now I need to find my y values for both of those situations. And I can use either equation. In fact, I'm going to use For the x equals 1, I'm going to use our red equation. Y is equal to negative 2 times 1 squared plus 16 times 1 minus 19. So y is equal to, well, this is just 1. 1 times negative 2 is negative 2. This is just 16. So plus 16 and then minus 19. And so I get y is equal to 14. 14 minus 19 is negative 5. So that gives me the point 1, negative 5. And now I'm going to use the blue equation for x equals 7. Y is equal to 18. And I don't know why, I just decided to. I don't have to. I could use the red one, I could use the blue one for both. It doesn't really make any difference. 7 squared, squared minus 144. They're going to be big numbers. Times 7 plus 121. Now, with those big numbers, it's going to be helpful to have a calculator handy. And I'm going to bring up the screen for the calculator here. If I forget to take this screen down, let me know. Okay. So I have 18 times 7 squared minus 144 times 7 plus 121. And if you use a calculator like this, and you get a y value of, and you get a solution here, you can just say y equals negative 5, and that's just fine. You don't need to do more steps here. This is fine. And so then our solution here is 7, negative 5. And what do folks notice that might be interesting about those two solutions? They have the same y value. And that's important because we're talking about quadratics here. So what this needs to look like is we have this one opens up because the a value is positive, and this one opens down because the a value is negative. So it's going to be something like this and like that. And our points of intersection are going to be 1, negative 5, and 7, negative 5. And another interesting thing here is going to be the fact that if we think about the line of symmetry, it has to be halfway between these 2 points because they have the same y value, which means that the vertices have to have the same x values. And the vertices have to be halfway between 1 and 7. So that means that this point right here has to be 4 something. I don't know what. I can figure it out. And this point right here also has to be 4 something. And we can figure that out as well. So that's kind of just something to notice. The question didn't ask us about it, but it's interesting and worth paying attention to. Questions on any of that? We are going to pause again and move our bodies. Anyone have a suggestion this time? Come on, somebody just say, oh, let's do, I don't know, whatever. No? Push-ups? All right, push-ups it is. I'll do that, Josh. Thanks for the suggestion. Let's do some push-ups, everybody. Now, this system, we're going to do another solving it algebraically, and it's two quadratics. So let's have a look at this. All of these are pretty much the same thing where we are using substitution to substitute that in for y. So we have 2x squared minus 16x plus 35 is equal to negative x squared plus 2x minus 2. All right. I'm going to move everything over to the left so I have a positive a value. No reason, doesn't have to be that way. Add x squared to both sides. Subtract 2x from both sides. Add 2 to both sides. We get 3x squared minus 18x plus 37 equals 0. Now, when I look at this quadratic, it's not the case that they're all divisible by anything. So we can't factor anything out. And it doesn't appear to me offhand that this is going to factor. So this is going to be a good candidate for using the quadratic formula. So I'm going to just highlight these coefficients, A, B, and C. And remember that the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4 a c all over 2a. All right? Those highlightings and the colors that I've chosen there may not match perfectly. I'm sorry about that. I'm doing the best that I can with the colors here. I think it's the background of the screen that makes it a little tough. But I do like the art this week, by the way, courtesy of another one of my AMC students. So not in this class, but I do enjoy the art. All right. X equals negative b. b is negative 18. Plus or minus. I'm going to have to squish this together a little bit, I think. There we go. The square root of b squared minus 4 times a. A is the 3 there. C is positive 37. All over 2a. Now, if you have a calculator like the TI-84 or you have some app like it, then you can just take care of the parenthesis or the underneath the square root there, kind of all in one. So we have negative 18 squared minus 4 times a times c, and we get negative 120. So we get x x is equal to positive 18. I'm going to scoot this down just a little bit. Plus or minus the square root of, and I can make that a little shorter, negative 120 all over 6. And what does this tell us right there? Oh, sorry, you can't see it. So what does this right there tell us? Yeah, it's a complex solution. Yep, yep. So there are no real solutions. And usually we're looking for real solutions, but we could simplify this complex number and we would get x equals 18 plus or minus 120. 120 is divisible by 4, and it's 30. Is 30 divisible by anything useful? Any other perfect squares? 3 and 10. Nope, doesn't look like it. So we can pull out the negative 1 underneath that square root. The square root of 4, let me do it this way. So this is going to be the square root of 4 times 30 times negative 1 over 6, which equals 18 plus or minus 2 square root 30. The I is not underneath the square root over 6. And I'm going to take all of that and I'm going to shrink it down a little bit so that I have just a tad more room here. Oh, the joys of digital math. And so I can rewrite that as x is equal to 18, 2, and 6 are all divisible by 2. 18 divisible by 2 is 9, or divided by 2 is 9. The 2 divided by 2 is 1, square root 30 I over 6 divided by 2 is 3. And that is pretty good. We could further rewrite it as 3 plus or minus square root 30 over 3i. So 9 divided by 3 is the 3, and then we have the square root 30 over 3 times I. Either one of those are perfectly good answers. Questions on that before we move on? Whoops. Where are we here? Geez, so many things open here. You got to see that I've been interested in Ken lately. Ken and Sudoku find a special place in my heart. All right. What does this mean about the graphs of these two? I got to get rid of this screen here. So what does this mean about the graphs? They won't intersect. That's what it means. Okay. So when there's no solution to a system of equations, the two graphs do not intersect. Now we have inequalities. And when we're talking about systems of inequalities, we're going to solve them graphically because there's going to be a region. The solution set will be a region. Okay? So I want to First, I'm going to graph the easy one of these, the line, negative x minus 1. Well, the b value there tells me that I have a y-intercept of 0, negative 1. And the slope of negative 1 tells me that I go down and to the right 1, down and to the right 1, or up and to the left 1. Just like that. I can connect those with as straight of a line as I can. And it's a solid line because there's an equal sign here. If there were not a solid line, there would not be an equal sign. Or vice versa. If there were no equal sign, it would not be solid, it would be dotted. Now, it says that y is greater than or equal to that line, which means I shade above the line. When it's y is greater than or equal to, it's above. When it's less than or equal to, it's below. So I'm going to shade here above the line. And I'm going to be kind of careful here. You should be kind of careful too. If you have colored pencils or pens, or if you want to use arrows because you don't have those colored pens or pencils around, then use arrows. And what I mean by that is something like this. If you do that, that's just fine instead of the shading. Now we need to graph that parabola. So the 2 here, the c value in standard form, tells me that I have a y-intercept of 0, 2, right there. Now I'm going to make a table to plot some points. I know that 0, 2 is on there because when I plug in 0 here and 0 there, this all makes a 0 plus 2, 0, 2. All right. Next, I'm going to plug in an x value of 1. So I have a 1 here and there. 1 squared is 1. So it's negative 1 here. Negative 1 plus 1 is 0. So all of that's 0 plus 2. So when x is 1, y is 2. Oh, that's interesting. That means that my line of symmetry is right here at x equals 0.5. Has to be halfway between these 2 points because they have the same y value. I'm going to next plug in an x value of negative 1. So negative 1 squared is positive 1, but this makes it negative 1. So this part's negative 1. Minus 1 is negative 2. Plus 2 is 0. So I have this point right there. Negative 1 is 0. And because this is the axis or line of symmetry, I know that I have to have a point reflected across that line. So for free, I get this point right there, which is 2, 0. Now, I don't know exactly where this point goes, but graphically, I'm not so worried about it. It goes somewhere right there, and I can go like that. Now, if there were a question that asked the question, is the point 0.5 2.3 a part of the solution set? We would have to check, but it isn't one of the questions here. Oh, that is not a solid line because there's no equal here, so that's a dotted line. Let me make that here. So similarly, if there were a question like, is this point right here a part of the solution, we would have to check it algebraically. But I can see that this is y is less than that parabola, so I have to shade below the parabola, so down here. Now, sometimes below or less than, it's confusing. Like, where is less than or where is below? And think of it this way. If there's any point, uh, if rain is falling down and it hits the parabola, all of this stuff under here is protected. So that's underneath it. Similarly, for this line, if rain is falling down and hits the line, all this down here is protected. So this is above it. All right. Questions on that problem before we move on to the last problem for the day? We're going to take one more break right now. It's been a lot of me talking, so breaks are important to keep that blood flowing. I'm going to do so. One thing I want to say before I move on is if I asked you, is the point 0, 0 in the solution set? The answer would be yes. Is the point 2, 2 in the solution set? The answer would be no, because it's on a dotted line, not part of the solution. Is the point 0, -1 a part of the solution set? Yes, it's on a solid line for the blue, and it's clearly in the red. So 0, -1 would be a solution. All right? So that's a way to think about the solution set as well. Questions there? All right, last problem for the day. Solve this system graphically. So, looking at the red quadratic, we have 0, -4 as one of our points. We're going to find some more points. I'm going to put in an x value of 1. So I'm going to plug in 1 for x. This is going to be 1 squared is 1 times 2, that's 2. 4 times 1, so we have 2 minus 4, that's going to be 2 minus 4, or excuse me, -2 minus 4 is -6. So we have 1, -6. Next, I'm going to pick an x value of 2. Whoops. And so I plug in 2 here, 2 there. 2 squared is 4. 4 times 2 is 8. Minus 4 times 2 is 8 minus 4. So that's going to be -4. And when I plot that point, I see right away, oh, that's good news. I now know that this is my axis of symmetry and this is my vertex right there on the axis of symmetry. So I also see that from my vertex, when I move left and right 1 unit, I go up 2 units to those points. That's because 1 squared is 1 times our a value of 2 is up 2. And you may not have done this last year. So we did this in my class. I want you to notice this pattern. It's a very nice thing to notice about quadratics. When I move to the left and right 2 units from the vertex, 2 squared is 4. 4 times 2 is 8. That means I go up 8 units. And those are additional points on my graph. And you can get points that way on a quadratic. It's a really nice way to graph using a quadratic. Once you have the vertex, you can just move to the left and the right, some number of units, square that value, and multiply by a. So it would be to the left and the right 3 units. 3 squared is 9. 9 times 2 is 18. So we would go up 18 units from those spots, and that would be another point. If you don't see that and you really want to, come see me during async. It's very, very handy for graphing quadratics. Here we have an equal sign, so it's got to be a solid line. Oops. A solid line. And because it's y is greater than or equal to here, we're going to shade above. So this is above. I'm going to be kind of sloppy here, not super careful, but you'll get the gist. All right. Now for the blue graph, well, check this out. I could rewrite this as x times the quantity x plus 3, right? Factoring out the x here, because x times x is x squared, and x times 3 is 3x. Well, this tells me that I have 2 x-intercepts. One of them is at 0, 0, because when I plug 0 in for x here, this all makes 0, so y must be 0. And I also have one at negative 3, 0, because when I plug negative 3 in here, this makes 0, which makes the whole side 0, and y equals 0. So that's helpful. The next thing I can do is I can pick a couple more points. I'm going to pick x equals negative 1 to find the y value. So when I plug negative 1 in there and there, negative 1 squared is 1 plus a negative 3. That's going to be negative 2. So I have a negative 1, negative 2. And that's nice because since these 2 points are the same y value, my axis of symmetry has to be right here, which means I get a point right there for free. So I'm going to add that point right there. And that's negative 2, negative 2. So what I'm doing there is I'm noticing things about the structure of parabolas in order to get points more easier. Structure in mathematics is really where a lot of the beauty is found, in my opinion. So because we do not have an equal sign here, it's a dotted line. And my vertex is going to be somewhere right here. It isn't too important exactly where it is. But so I'm going to just estimate. And because it is greater, y is greater than that parabola, we're going to shade above again. And so you can see the solution set is this area in here. And this -1, +2 would be in the solution set because it's on the solid line. 0, 0 would not be in the solution set because it's on the dotted line. 0, 3 is clearly right in the middle of the solution set. So here's a question I want to ask. Will this blue part of this blue parabola ever intersect with this part of this parabola as they go on forever? This parabola has an a value of 2, which means it's squished together. This parabola, the blue one, has an a value of 1. So it will, in fact, eventually intersect. Eventually. But it's going to happen way up there. Okay? So outside of that, so we're only where they overlap will the solution set exist. Are there questions? We have like 3 minutes left. I told you it was going to be a lot of me talking today. All right. Well, thanks for being with me today.